Hi, I'm Gary, and I want to show you how I use Cloudy. Today, I'm going to talk about the grid command, one of the most heavily used commands we have. It's described in an entire chapter in Hazy 1. The secret here is you specify one of the input parameters. We've used a hydrogen density command in the models we've talked about. So HDen takes as an argument the log of the hydrogen density. If you add the vary option, that tells the code you want to vary the hydrogen density. Then you have to combine that with a different command. I normally write them side by side, but that's not required. The grid command. So grid acts like a for loop or a do loop in a programming language. So you specify a lower limit, an upper limit, and an increment. So what it does is farm off in cloudy models and puts it one on a core. So this is an embarrassingly parallel simulation. So the if you can allocate 20 good cores and you've got 20 models, then the grid will take as long as one core takes. Cloudy is a unique code in that because of its huge atomic data needs, it's constantly pulling data from cache and putting it back in, putting the data back out. So the execution time for Cloudy is very, very largely memory limited, cache limited. So bigger caches helps a lot. And so hitting a computer with a lot of cores isn't necessarily going to get you in cores performance. And there's a special case is the hyperthreads. Hyperthreads, in my experience, don't get you very much at all. The danger here is if you hit your machine with 30 cloudies all at one time, one on each core, each one of these cloudies may take half a gigabyte, depending on how big your model is. If you turn up the databases to their full extent, Cloudy becomes 10 times bigger than it is in its default state. But in its default state, we only include as much atomic data as you need in most cases. That's a judgment call. But there are options to make much more complete models with much, much more data. And you can easily hit the memory limit of the computer. Modern computers don't stop. They thrash. They try to use the disk for memory. And in my experience, basically you have to cycle the power on the computer in that case. So just be mindful of how many cloudies you're running at one time and how much memory you have. So the grid commands habitually use the last option. You only want the last iteration. If you're doing several iterations to converge the optical depth, you want the last iteration. And for historical reasons, a hash mark is placed between different models in a grid run. In most cases, we don't want it. And so the save commands include the no hash option. There are other options for the command. You can add a sequential keyword to the grid command, and it'll just do it one model per core. We use that in the test suite. And you can also specify the number of cores you're willing to allocate. So if your system appears to have 20 cores and 10 are hyperthreads, maybe you just want to use 10. So you would specify the lower upper increment values and then the number of cores as an optional fourth parameter. And there's a separate option on save, which tells the code not to do a gather at the end of the calculation. The code will bring all the output files from the n cores together as if they were done sequentially into one file. In big calculations, that can take longer than the run itself because it has to move a lot of files around on disk. So let's have a look at how this works and compute one. So this is my subdirectory, and I've already set up a grid file. So let's say prefix, I'm going to call the save files grid. Coronal equilibrium we haven't talked about, but it does a model in collisional ionization equilibrium, something like the corona of the sun. So this is a a limit where you're going to ignore photoionization. It's just going to be some external agent has set up a temperature. Mostly temperatures can be entered as logs in Cloudy. We'll talk about the input deck format in a different video. So this would be a coronal equilibrium at 10 to the 6 Kelvin. That number needs to be there to get past a parser, but it's not used for anything. The vary command occurs on this line, so it says you're going to vary that number. And then the next command is the grid command. So the temperature, low temperature will be 100 Kelvin, log T of 2. The high temperature will be 10 million Kelvin. And then in these log increments will be 0.5 dex. So that sounds like 12 or so computer models on this grid. If we're going to set a hydrogen density of 0, we're not going to change that. This pair of commands here are used habitually if you want to compute what's called a unit cell. If you want to compute 1 cubic centimeter and figure out the properties of 1 cubic centimeter to be optically thin, you would make the zone, just have one zone and make it 1 centimeter thick. So set dr sets the log of the zone thickness in centimeters to be one zone. Now, this is the cosmic ray background command. You have to have this, absolutely have to have it for the chemistry to work because you need a source of ion molecules in the chemistry. We don't want too much of galactic background because it will overwhelm the thermal equilibrium. We'll come back and talk about that in a different video. So cosmic rays background takes the background for the galaxy. It does vary from spot to spot, but it's somebody's mean background. And this is going to set the cosmic ray background ionization rate to 10 to the minus 4 of the galactic background. So cosmic ray is an ionized gas, a heats ionized gas. In neutral or atomic gas or molecular gas, it will create secondary ionizations. Iterate, print last iteration, we've seen those. Now we're going to save the grids. We'll look at the grid file in just a bit and see what's in there. It's a critical file for this. Last no hash always appears. And then save cooling, the command we haven't talked about yet, but we'll see the output in just a second. So let's get out of that. And I'm going to run Cloudy. So off it goes. It's cooking. Let's go off to a different window here and run the top command and see what's going on. So you see here, there's a whole bunch of Cloudies running. Each one of these, I don't see the memory, oh, there it is, about a quarter of a gigabyte, a little under 200 megabytes. So we've got as many Cloudies as cores on this computer. This is a Mac Mini, so it has of order a dozen cores. And they're all running, they're all doing their best. And when they finish, we come back here. It's done. So let's look at what we have. Grid star. Okay. So here is the grid save grid command. Let's look at that. Let's do a pasteboard copy and look at this in Excel. So this is what's in the grid command. So this is the index in number of cores that we're using. So we see there are 12 cores running, or 13 because it starts from 0. This is the failure flag. It's one of the flags that Cloudy announces at the end. This is a warning flag. So if there's a failure or a warning, your calculation's in deep trouble. So the code is autonomous and self-aware, so it does a lot of self-checking. And if these flags are false, which they are, things are good. This is the exit code. That's also okay. This is the values for the grid. So that we specified the grid as a temperature grid, and we started at 10 to the 2, 10, and went to 10 to the 8, so it's 10 to the 2, 10 to the 2.5, 10 to the 3, 10 to the 3.5. So this is a good grid calculation, and we can go on from there. Okay, The next thing we want to do is look at the cooling. So the reason I was doing this was a quick and dirty look at a cooling function. We'll do far better than this when we come back and talk about the cooling function in the physics part of the discussion. But I'll do a pasteboard copy from grid.col, go back to Excel. So we have here, this is the depth of the model. So that these are there are many different models. The temperature and linear temperature is given in this column. So we can see we started at 100 Kelvin and went up to 10 to the eighth Kelvin. This is the heating, which is not used for anything in this model because we set coronal equilibrium. The heating would be some kind of mechanical heating, passing shock waves, something like that. And this is the cooling, which is what you want for the cooling function. So let's take this, sorry, temperature, make that the independent axis. Here's the cooling, and let's insert a chart using these two. So there's our chart. We can't see much because it's linear scale. There we go. And so what we see here is kind of a classical interstellar medium cooling function. The temperature down at 100 Kelvin is low. It reaches a peak at about 3,000, 4,000 Kelvin. Then it comes back down, and then it reaches the global peak at about 10 to the 5 Kelvin, comes down, and then starts to go up. We'll come back and talk about that. In the M16 sim, when you went into the PDR, there was a thermal front, and that was caused by this inflection in the cooling function. It's a physically meaningful front. And mathematically, what happens is in one region of gas, it's up on this branch of the cooling function. And when it needs to cool down more, it has to jump physically, mathematically over to the other branch of the cooling function. So it happens mathematically in one zone, it changes gas phase. So with that, we'll use the grid command a lot. This is one of the most heavily used commands, and it's a very, very powerful and a great way to get a lot of things done. Thank you.